Hello everyone, this is Nirali Patel from New Alger Institute of Engineering and Technology. In today's lecture, we are going to discuss about expected values of two-dimensional random variables. After that, we will see properties of expected values of two-dimensional random variable. Then we will see about conditional expectation and conditional variance for continuous random variable as well as for the discrete random variable. And then we will see about the properties of conditional expectation. After that, at the last, we will discuss about examples on this topic. So let's get started. So the first topic is that expected values of the two-dimensional random variable. So if x comma y is two-dimensional discrete random variables with joint probability mass function p of xi comma yi is equals to pij, then the mathematical expectation of a function g of xy is given by e of g of xy is equal to sigma j is equal to 1 to infinity, sigma I is equal to 1 to infinity, g of xi yj into pij. So now we know that this pij is nothing but f of xy. So in more general, we can write sigma x summation on y g of xy into f of xy. So this is the expected value for the discrete random variable. Now for the continuous random variable, if x and y is two-dimensional continuous random variable with joint probability density function f of xy, then the mathematical expectation for function g of xy is given by e of g of xy integration from minus infinity to infinity, again integration from minus infinity to infinity g of xy into f of xy dx dy. So this is the expected value for the two-dimensional random variable xy, where the function for that two-dimensional random variable xy is given with g of xy. That means this function is the function for the random variable x and y, such as x square y, or we can say the x plus y or x plus 3y, any function that contains both random variable x and y. Similarly for the discrete random variable as well. Now let's see the properties of this expected value for the two-dimensional random variables. So if x and y are random variables, then e of x plus y is equal to e of x plus e of y, provided all expectation exists. And if x and y are the independent random variables, then we can say e of xy is equal to e of x into e of y. Now the next is conditional expectation and the conditional variance. So if x and y is the two-dimensional discrete random variable and g of xy is the function for this two-dimensional random variable, and the joint probability for this two-dimensional discrete random variable is given with p of ij. So that is nothing but joint probability mass function. Then the conditional expectation is given by e of gxy, where y is equals to yj is already given. So that is equals to sigma I is equals to 1 to infinity g of xi yj into probability of x is equals to xi when y is equals to yj is already given. So as we have discussed the concept of conditional probability, that some event is already occurred, then what is the probability of occurrence of any given suppose event A. Similarly over here, the sum y is equals to yj is already given. Now what is the expected value for g of xy? So that is given with this formula. Now we know that the probability of this x is equals to xi given y is equals to yj is nothing but p of x is equals to xi and y is equals to yj in upon p of y is equals to yj, where this p of y is equals to yj is nothing but probability mass function for variable y. So in general, we can write sigma I is equals to 1 to infinity g of xi comma yi pij. This can be written as pij upon p star j. So this is nothing but the probability mass function for variable y. Now, in particular, if we want to find out the conditional expectation of discrete random variable x, over here this function is made up of two variables x and y. But if we want to find out the conditional expectation for random variable x given by y is equal to yj, then it is given with this formula E of x given y is equals to yj is equals to summation from I to 1 to infinity xi p of x is equals to xi given that y is equals to yj is already occurred. So here there is a function of this x and y random variable, but here we want to find the expected value for the random variable x. So here this g of xi yj is nothing but replaced with the xi, and this is as it is. Now the conditional variance of x given y is equals to yj is given by variance of x given y is equals to yj. Then we know that the variance of x is E of x minus mu whole square. So from that we can write E of x minus mu. So the mu is nothing but the expected value. So that is E of x given y is equals to yj that we have already discussed over here whole square given that y is equals to yj. So that is the conditional variance of variable x given that y is equals to yj. Now, if x and y is the two-dimensional continuous random variable with joint probability density function f of xy, then the conditional expectation for function g of xy, where function g of xy is the function of random variable x and y, is given by e of g of xy, given that y is equals to y. Integration from minus infinity to infinity, g of xy, f of x given y into dx. So this f of x given y is nothing but that is f of xy upon marginal probability mass function of variable y, marginal probability density function of variable y. So that is equals to integration from minus infinity to is f of x comma y marginal density function of variable y. So we can write g of xy f of x y upon f of y, and here the y is already occurred, so this is nothing but the marginal probability density function for variable y. Now if we want to find the conditional expectation of x given y is equals to y, so in that case we have to write e of x given y is equals to y. Now here we want to find the only expected value for the x, so instead of g of xy we can write the x only and the remaining is as it is. Similarly, expected value for the variable y given x is equals to x. So that is integration from minus infinity to infinity y into f of xy dx upon f of x, where x is already given. So this is nothing but the marginal probability density function for variable x. Now the conditional variance of variable x is given by variance of x given y is equals to y is equals to expectation of x minus expectation of x given y is equals to y whole square given y is equals to y. Similarly, the variance of y given that x is equals to x, so that is given by e of y minus e of y given x is equals to x whole square given that x is equals to x. So that is the about the conditional expectation and the conditional variance. Now let's see the properties of the conditional expectation. So if x and y are two independent random variables, so e of y given x is equals to e of y, and e of x given y, that means the expectation of x given y is equals to expectation of x. If expectation of x into y is given, so that is nothing but the expectation of x into expectation of y given x. And the expectation of x square y square is equals to expectation of x square into expectation of y square given x. So this is all about the conditional expectation properties. Now moving to the example. So let x and y be two random variables, each taking value -1, 0 and 1. So these are the values for the random variable x and y respectively. Having the joint probability distribution is given below. So over here the joint probability distribution is given. Show that the x and y have a different expectation. So first we have to find the e of x. So that is nothing but sigma xp of x. So that is the value of x is -1 and that is -1 into 0.2, then 0 into 0.4 plus 1 into 0.4. The answer is 0.2. Now E of y. So that is sigma y into E of y. So that is -1 into 0.2 plus 0 into 0.6 plus 1 into 0.2. So the answer is 0. So here the E of x is not equal to E of y. So the x and y have a different expectation. Now find the E of xy. So E of xy is equal to sigma xi yj into Eij. So the xi value is -1 and -1. That time the value of Eij is 0, so 0 plus -1 into 0, so -1 into 0, and that time that is 0.2 plus -1 into 1, and that time that is the 0 plus 0 into -1, and that time the probability is 0.1, then 0 into 0, that time probability is 0.2 plus 1, 0 into 1, and that time probability is 0.1. Then 1 into -1, and that time probability is 0.1. Then 1 into 0, and that time probability is 0.2. Then 1 into 1, and that time the probability is 0.1. So this would become 0. This is also 0. This is also 0. This 0. This is also 0. This is also 0. This is also 0. So, and minus 0.1 plus 0.1. So the answer is 0. Now the next thing that we have to find is variance of x and the variance of y. So we know that the variance of x is nothing but E of x square minus E of x whole square. So we have the value of E of x square. So let's first find the E of x square. So for the E of x square, so that is sigma x square into P of x. So -1 square into 0.2, then 0 square into 0.4 plus 1 square into 0.4. So this would become 0.2 plus 0 plus 0.4. So the answer is 0.6. So minus 0.6 minus 0.2 square. So that is 0.4. So the 0.04. So the variance is 0.56. So this is the variance of x. Similarly, we can find the variance of y. So that is nothing but E of y square minus E of y whole square. So over here, we have the value of E of y. Now let's find out the E of y square. So that would become -1 square into 0.2 plus 0 square into 0.6 and 1 square into 0.2. So this would become 0.2 plus 0.2. So the answer is 0.4. And E of y square is 0.4 and E of y is 0. So the variance of y is 0.4. Now the next thing that we have to find, that given that y is equal to 0, what is the conditional probability distribution of x? So for that probability distribution, given y is equal to 0. So for first we have to find out for the x is equal to 0. So that is equals to P of x is equal to 0, y is equal to 0 upon P of y is equal to 0. Now, for the P of y is equals to 0, that is 0.6. And for the x0 and the y0, that is 0.2. So, zero point 0.2 divided by 0.6, that is 1 by 3. Similarly, P of x minus 1 when the y is 0. So, P of x is equals to minus 1 given that y is equals to 0. So, that is P of x is equals to minus 1 and y is equals to 0 upon P of y is equals to 0, which is equals to, now for the x is equals to minus 1 and the y is equals to 0, that is also 0.2. So, 0.2 divided by, and for the y is equals to 0, that is 0.6 only. So, that is also 1 by 3. Similarly, P of x is equals to 1 given y is equals to 0. So that is equals to P of x is equals to 1 and y is equals to 0 upon P of y is equals to 0. Now for the x is equals to 1 and y is equals to 0, the probability is 0.2. So 0.2 divided by 0.6, the answer is 1 by 3. Now coming to the next example, so it is given that two random variables have joint probability density function f of x is equals to xy upon 96 when x lies between 0 and 4 and y lies between 1 and 5, otherwise it is 0. So first find out a of x. So that is nothing but minus infinity to infinity, integration from minus infinity to infinity, x into f of xy dx dy. So minus infinity to infinity. So here this is y is defined from 1 to 5. So let's keep it from 1 to 5 and x is defined from 0 to 4. So this keeps as integration from 0 to 4. X into xy upon 96 dx dy. So this is integration from 1 to 5 and 1 by 96 become common. Y as it is and this is x cubed by 3. Upper limit is 4 and the lower limit is 0 dy. So that is equals to 1 by 96 integration from 1 to 5 y 64 divided by 3 dy. So 64 divided by 3 become common because it is constant and this is y squared divided by 2 and the lower limit is 1, upper limit is 5. So 64 divided by 3 into 96, 25 upon 2 minus 1 by 2. So that would become equal to 64 into 24 upon 3 into 96 into 2. So the final answer would become 8 by 3. This is the value for E of x. Now for the E of y. So E of y is nothing but integration from minus infinity to infinity, again integration from minus infinity to infinity, y into f of xy dx dy. So here the y exists from 1 to 5. So integration from 1 to 5 and x exists from 0 to 4. Y into xy divided by 96 dx dy. So this will become integration from 1 to 5. 1 by 96 would become common. Y into x square divided by 2. 0 to 4 limit and dy. So 1 by 96 integration from 1 to 5 y into 16 divided by 2 dy. So that would become 8 divided by 96 integration from 1 to 5 y dy. Sorry, that would here y square because y into y, here also y square and here also y square. So 8 divided by 96 y cube divided by 3. Lower limit is 1, upper limit is 5. So 8 divided by 96 into 3 into 124. So the final answer is equals to 31 divided by 9. So this is the value of E of y. Now the next thing that we have to find is E of x into y. So E of x into y is integration from minus infinity to infinity. Again integration from minus infinity to infinity. Xy into f of xy. So that is xy divided by 96 dx dy. So 1 by 96 would become common. Now y exists from 1 to 5 and x exists from 0 to 4. X square y square and dx dy. So 1 by 96, 125, x cube divided by 3, y square. And here the lower limit is 0 and the upper limit is 4 d1. So 1 by 96 into 16 divided by 3, integration from 1 to 5, y square d1. For that, 1 by 96 into, this would become 64 because 4 is to 3, so 64 into 64 divided by 3, then 5 cube divided by 3, lower limit is 1, upper limit is 5. So the answer for that is equals to 1 by 96 into 64 divided by 3 into 124 divided by 3. So the final answer is equals to 248 divided by 27. Now the next thing that we have to find E of 2x plus 3y. So E of 2x plus 3y is equals to 2 into E of x plus 3 into E of y. So the 2 into E of x is 8 by 3 plus 3 into E of y is equals to 31 by 9. So this would become 3. So 16 plus 31 divided by 3. So the final answer is 47 divided by 3. Now the next thing that we have to find is variance of x. So the variance of x is E of x square minus E of x whole square. And the variance of y is equals to E of y square minus E of y whole square. We have the value of E of x and the E of y. To find out the variance of x and the variance of y respectively, let's first find out the E of x square and the E of y square. So E of x square is integration from minus infinity to infinity, again integration from minus infinity to infinity, x square into f of xy, that is xy divided by 96 dx dy. So the y exists from 1 to 5 and x exists from 0 to 4, x cube y and 1 by 96 would become common dx dy. So 1 by 96 integration from 1 to 5, x raised to 4 upon 4, upper limit is 4, lower limit is 0, y dy. So that is equals to 1 by 96 into 256 divided by 4, integration from 1 to 5, y dy. So 256 divided by 96 into 4, y square divided by 2, lower limit is 1, upper limit is 5. So 256 upon 96 into 4, 24 divided by 2. So the final answer is equals to 8. Now E of y square. So E of y square is minus infinity to infinity, again integration from minus infinity to infinity, y square into xy by 96 dx dy. So 1 by 96 would become common. Now y exists from 1 to 5 and x exists from 0 to 4. xy cube dx dy. So 1 by 96 integration from 1 to 5, x square divided by 2, lower limit is 0, upper limit is 4, y cube dy. So 1 by 96 into 16 divided by 2, integration from 1 to 5, y cube dy. That is equals to 16 upon 96 into 2, y raised to 4 upon 4 into 1, lower limit and the 5 is upper limit. 16 upon 96 into 2, 625 minus 1 divided by 4. So the final answer is equals to 30. So now let's just put the value over here. The E of x square is 8 and E of x whole square. So that means 16 4 divided by 9, which is equals to 8 by 9 upon and variance of y. So the E of y square, so the E of y square is 13 minus E of y, that is 31 minus 9 whole square. So the final answer is equals to 92 divided by 81. So this is the variance of x and y respectively. Now the next thing that we have to find is covariance of x. So covariance of x y is equals to E of xy minus E of x into E of y. So E of xy is nothing but that is 248 divided by 27 minus E of x. So the E of x is 8 by 3 and E of y is 31 by 9. So the final answer of covariance of xy is equals to 0. So this is all about today's lecture. In next lecture, we are going to discuss about Chebyshev inequality. Till then, keep exploring and thank you.